The space between stars is not empty. It holds the keys to the universe's greatest mysteries. Every star you see, every world that might harbor life, and every galaxy spinning across the cosmos emerges from a single shadowy substance, the interstellar medium. This vast, diffuse mixture of gas, dust, cosmic rays, and magnetic fields fills our galaxy and connects everything. Yet after decades of study, it still guards secrets that challenge the very foundations of astrophysics and star formation. By the end of this journey through 25 of the most compelling puzzles, you will see how the unseen space between stars actually shapes the fate of the universe and your place within it. Why does most of the normal matter in the universe seem to be missing? And who or what hides among those ghostly absorption lines that have defied identification for nearly a century? What do you think truly lies between the stars? For decades, we have treated interstellar dust as little more than cosmic grime. But these microscopic particles may be the most chemically complex material in the galaxy. Each grain is a tiny factory, a catalyst for the formation of molecules and the birthplace of new stars. And yet, despite their profound importance, we still do not know exactly what they are made of. We can infer their composition from the way they absorb and scatter starlight. When light from a distant star passes through a cloud of dust, certain wavelengths are blocked, leaving a kind of fingerprint in the spectrum. From this, astronomers have identified the main ingredients: silicates, the same rocky minerals found on Earth, carbonaceous materials similar to soot or graphite, and icy mantles of water, carbon dioxide, and ammonia that freeze onto the grains in the coldest regions. But this is only a rough sketch. The exact proportions of these components remain uncertain, and we have barely begun to catalog the complex organic compounds that might be present. One of the biggest challenges is that interstellar dust grains come in a wide range of sizes, from molecules a few atoms across to particles as large as a micrometer. Their size distribution dramatically affects how they interact with radiation and how they clump together to form planets. But our models of this distribution are based on indirect measurements and assumptions that often conflict with newer observations. For example, infrared spectroscopy, our most powerful tool, can reveal the presence of certain chemical bonds, but it cannot tell us the full molecular structure. We see a broad absorption feature near 3.4 micrometers that suggests the presence of aliphatic carbon compounds, but we cannot say exactly which ones. And there are other, weaker features that have no clear identification at all. This uncertainty ripples through all of astrophysics. If we do not know the true composition of dust, we cannot accurately correct for its obscuring effect when we measure the brightness of distant galaxies or supernova. We cannot properly model how dust grains form and grow in the outflows of dying stars. And perhaps most critically, we cannot understand the role these particles play in the chemistry of star-forming clouds. Complex organic molecules, the building blocks of life as we know it, may be created on the surfaces of these grains, and the diversity of those molecules depends on the exact mix of materials available. The dust itself is a living archive carrying the chemical fingerprint of every star and supernova that has contributed to it over billions of years. To read that archive, we need better observations and more sophisticated models, but what we have already discovered raises a tantalizing question. If the unseen space between stars is filled with such intricate and poorly understood chemistry, what other secrets could be hiding in the shadows of those tiny specks? Half the ordinary matter in the universe is nowhere to be found. Astronomers have spent decades tallying up every star, every galaxy, every cloud of gas, and every speck of dust they can see. And when they add it all together, the total comes up far short of what the laws of physics demand. This is the mystery of the missing baryons. Baryons are the protons and neutrons that make up you, the Earth, the stars, and everything you can touch. They are the normal matter of the universe, as opposed to the dark matter that lurks invisibly. And according to our best models of the early universe, there should be a certain amount of this ordinary stuff left over from the Big Bang. But when we count it all in the local universe, the present day, we only see about half of it. The other half is simply unaccounted for, so where did it go? The leading candidate is a vast, tenuous network of gas known as the warm-hot intergalactic medium, or WIM. This gas is spread thinly between galaxies, and it has been heated to temperatures between 100,000 and 10 million degrees by shock waves from galaxy formation and the energy from active black holes. At those temperatures, the gas glows mostly in X-rays, but it is so diffuse that its emission is almost impossible to detect directly. Instead, astronomers search for it by looking at how it absorbs light from distant quasars and gamma-ray bursts. When a beam of light passes through a patch of WIM, the atoms in the gas leave their signature in the spectrum, a faint absorption line. Finding these lines is extremely difficult because the gas is so spread out and the signals are weak. But in recent years, observatories like the Chandra X-ray Observatory and the European Space Agency's XMM Newton have started to pick up hints of this hidden reservoir. Even with these successes, the mystery persists because the WIM is not the whole story. Within our own galaxy, the interstellar medium is expected to contain a warm-hot phase as well, gas heated to similar temperatures by supernova explosions and stellar winds. This component should hold a significant fraction of the Milky Way's baryons, yet detecting it has proven just as elusive. The gas is too hot to form molecules, too thin to emit much light, and too scattered to leave strong absorption signatures. Scientists are now designing new X-ray and ultraviolet telescopes with higher sensitivity to finally track down these missing atoms. Why does this matter so much? Because the baryon cycle is the engine that drives galaxy evolution. Gas flows into galaxies from the intergalactic medium, cools, forms stars, and then gets blown back out by supernova and black holes. If we cannot account for half the raw material, we cannot truly understand how galaxies like our own were built. The missing baryons are not just a loose end in a cosmic budget. They are the invisible threads that connect galaxies to the larger web of the universe. And until we find them, our picture of how the cosmos works will remain frustratingly incomplete. Almost a century ago, astronomers noticed something strange in the light of distant stars. When they spread that light into a spectrum, they saw hundreds of faint absorption lines that did not match any known atom or molecule. These features became known as diffuse interstellar bands, and they have haunted astrophysics ever since. The mystery is simple on the surface. Something in the space between stars is absorbing specific wavelengths of starlight, but we have no idea what that something is. The lines are broad and diffuse, hence the name, and they appear in the spectra of virtually every star that shines through a significant amount of interstellar material. They are not caused by the stars themselves because they vary in strength depending on how much gas and dust lies along the line of sight. The carriers must be widespread across the galaxy, stable enough to exist in the harsh environment of space, and yet elusive enough to defy identification for generations. The hunt for the culprits has been one of the longest-running detective stories in astronomy. Over the years, hundreds of candidate molecules have been proposed and ruled out. The leading suspects today are complex carbon-based structures. One family of candidates is the polycyclic aromatic hydrocarbons, or PAR. These are large, flat molecules made of fused rings of carbon atoms, similar to the soot produced by burning wood or coal on Earth. PAHs are known to be abundant in interstellar space because their infrared emission is seen in many regions. They are strong absorbers of ultraviolet and visible light, and their spectra show a forest of broad features that could potentially match some of the diffuse interstellar bands. But the problem is that no single pH molecule can account for all the observed bands. and the exact wavelengths depend on the shape, size, and charge of the molecule. Another class of suspects is the fullerenes, the hollow carbon cages like Buckminster fullerene, which is a sphere of 60 carbon atoms. Fullerenes have been detected in space, and their absorption properties have been studied in the lab. Some of their spectral lines align with a few of the mysterious bands, but again, not all. Other researchers point to long carbon chains, molecules like cyanopolyenes that stretch out in straight lines of alternating carbon and nitrogen atoms. These chains are known to exist in dense molecular clouds and have strong absorptions in the visible range. However, matching the exact positions and widths of the diffuse interstellar bands requires laboratory spectra taken under conditions that mimic the cold, low-pressure environment of space. That is easier said than done. Creating and isolating these molecules in the lab is a formidable challenge. Even when they can be made, their spectra depend critically on temperature, which in interstellar space can be as low as a few tens of degrees above absolute zero. To complicate matters, the carriers may not be neutral molecules. Ions, charged versions of these same compounds, have different absorption patterns. And there could be multiple carriers, each responsible for a subset of the bands, which would explain why no single substance fits all the lines. Recent observational surveys, using powerful telescopes to capture high-resolution spectra of many stars along different lines of sight, have revealed that the strengths of different diffuse interstellar bands vary independently. This suggests that the carriers are different molecules distributed unevenly through the galaxy. Some bands are stronger in regions with more ultraviolet radiation, while others dominate in darker, denser clouds. This spatial variation gives clues about the chemical nature of the carriers, but it remains a puzzle that laboratory astrophysicists and observational astronomers are working together to solve. They compare spectra from the lab with spectra from telescopes, searching for any match that survives statistical scrutiny. So far, only a handful of the hundreds of bands have been tentatively assigned. The rest remain ghostly signatures of an unknown identity, and this mystery is not just a curiosity. The diffuse interstellar bands are a window into the rich organic chemistry that occurs between the stars. The very molecules that may be responsible for these absorption lines could be the same ones that seeded the early solar system with the raw materials for life. By unlocking their identity, we may learn not only what lies in the shadows of starlight, but how the building blocks of biology are forged in the cold, vast spaces of the galaxy. Hidden among the gas and dust, an invisible force shapes the destiny of every star. Magnetic fields thread through the entire interstellar medium, wrapping around clouds, guiding the flow of charged particles, and resisting the collapse of matter into new suns. Without them, star formation might operate entirely differently, and the galaxy itself would lack the structure we observe. Yet despite their profound influence, we have only the faintest map of these fields. Their strength varies wildly from one region to another, and their three-dimensional topology, the way they twist and coil through space, remains one of the most stubborn unknowns in astrophysics. Measuring a magnetic field that is both weak and spread across light years is no small task. Astronomers rely on a handful of indirect techniques, each with its own limitations. One of the oldest is Zeeman splitting. When atoms sit inside a magnetic field, their energy levels split, causing spectral lines to separate into multiple components. The amount of separation tells you the strength of the field along the line of sight, but this signal is tiny, often just a few thousandths of a nanometer, and it only works for clouds where certain molecules like hydroxyl or atomic hydrogen are abundant. For most of the interstellar medium, the signal is simply too weak to detect. Another method uses Faraday rotation. When a polarized radio wave passes through a magnetized plasma, its plane of rotation twists. By measuring how much the rotation changes at different wavelengths, scientists can infer the magnetic field strength and direction integrated along the entire path. This technique has given us beautiful maps of the galaxy's large-scale field, but it averages over vast distances and cannot reveal the fine details within a single cloud. Dust polarization offers yet another window. Elongated dust grains tend to align with the local magnetic field like tiny compass needles. When background starlight passes through them, it becomes polarized. By mapping that polarization across the sky, we can trace the field's direction in the plane of the sky. Observations from missions like the Planck satellite have produced stunning all-sky maps, but they still lack the depth information needed to build a true three-dimensional model. The central puzzle goes deeper than just measurement difficulty. How are these fields generated and maintained across such enormous scales? Magnetic fields decay over time unless something reinforces them. In stars and planets, internal dynamos do the job, but the interstellar medium has no single rotating core. Instead, the field appears to be amplified by turbulence and shear motions in the gas, a process that is poorly understood both theoretically and observationally. Supernova shocks, galactic rotation, and the chaotic churn of star-forming clouds all contribute, but the exact mechanisms that sustain fields over millions of years remain speculative. This mystery is tightly linked to the next great puzzle of the interstellar medium, turbulence. Just as the magnetic field threads through the gas, turbulence stirs and mixes it, creating a cascade of energy across scales. Without understanding the interplay between magnetic fields and turbulence, we cannot hope to model star formation or cosmic ray transport with any confidence. The two forces are locked together, and measuring one without the other gives only half the picture. And as we will see, turbulence itself hides its own deep secrets. Turbulence in the interstellar medium is a hidden hurricane that never stops. Imagine the space between stars as a vast, churning ocean. Currents of gas and dust swirl in patterns that span hundreds of light years, driven by violent events and the slow grind of the galaxy's rotation. This chaotic motion is not random noise. It is the engine that transfers energy across scales, breaking up clouds into smaller fragments that can eventually collapse into stars. Without turbulence, star formation would proceed very differently, perhaps not at all. Yet despite its central role, the origin and nature of this turbulence remain deeply mysterious. One of the biggest puzzles is where the energy comes from. Turbulence dissipates quickly, especially in the diffuse gas where it moves in fast supersonic flows. To keep the interstellar medium churning, there must be constant sources of new energy. The leading candidates are supernova explosions, which unleash enormous shock waves that slam into surrounding gas and set it spinning. Stellar winds from massive stars also inject momentum, blowing bubbles and stirring the cloud around them. And on the largest scales, the galaxy's own rotation creates shear forces that stretch and twist the gas into turbulent patterns. But it is not clear which of these mechanisms dominates at different scales or in different regions. Observations show that turbulence in dense molecular clouds is often weaker than in the diffuse medium, hinting that energy is injected mainly at large scales and then cascades downward, much like the way a storm system breaks into smaller eddies. But the exact efficiency of this cascade and how magnetic fields modify it are still areas of active debate. The real challenge is measuring turbulence directly. We cannot see the motion of individual gas parcels the way we can track a leaf on a river. Instead, astronomers rely on the Doppler shift of spectral lines. When a cloud of gas moves toward or away from us, the light it emits or absorbs shifts in wavelength. The width of a spectral line gives an indication of the range of velocities within the cloud. A broad line suggests strong turbulence, but this is only an average. It cannot tell us how the turbulence varies within the cloud, nor can it distinguish between large-scale ordered motion and true random turbulence. Worse, the gas we observe is often not the only component. Along the line of sight, there may be multiple clouds moving at different speeds, blending their signals into a confusing mess. This is known as the velocity crowding problem, and it makes interpreting narrow line widths extremely difficult. To overcome these limitations, scientists build numerical simulations. They model the interstellar medium as a compressible, magnetized fluid and watch how turbulence develops when they inject energy from supernova or stellar winds. These simulations are beautiful and complex, showing filaments, knots, and waves that look remarkably like real observations. But when we try to match the simulation results to actual data, discrepancies appear. For example, simulations tend to produce slightly different statistical properties, like the distribution of density fluctuations, than what telescopes actually see. Part of the problem is that real turbulence in the interstellar medium is compressible, meaning the gas changes density dramatically as it moves. Unlike the incompressible turbulence you see in a river, where water is nearly constant density, interstellar gas can be compressed by shock waves into dense clumps that are 1,000 times denser than their surroundings. This compressibility introduces a whole new layer of physics that is difficult to capture accurately in models. Another major complication is the role of magnetic fields. Turbulence and magnetic fields are deeply intertwined. The field can suppress turbulent motions perpendicular to its direction, creating an anisotropy that is hard to measure. Meanwhile, turbulent motions can twist and amplify the field, feeding back into the dynamics. This dance between gas pressure, magnetic pressure, and turbulence is known as magnetohydrodynamic turbulence, and it is one of the most complex phenomena in astrophysics. There is no complete theory for it, only approximations and simulations that often disagree on key details. Despite these challenges, one thing is becoming clearer. Turbulence likely governs the critical transition from diffuse, low-density gas to the dense cores where stars are born. Without turbulence, a cloud would simply collapse under its own gravity, forming stars all at once. But the random motions of turbulence create a network of shocks and compressions that fragment the cloud into many smaller pieces, each one reaching the point of collapse at a different time. This fragmentation sets the initial mass function, the distribution of star masses, which is one of the most fundamental unsolved problems in astronomy. So understanding exactly how turbulence breaks up a cloud and how it interacts with cooling and magnetic fields is not just an abstract pursuit. It is the key to explaining why stars form in clusters, why they have a range of masses, and why some clouds give birth to many stars while others remain barren for millions of years. The turbulence that seems so chaotic may actually be the sculptor that shapes the destiny of every stellar nursery. And as we look deeper into these swirling currents, we find that even the densest clouds hide a final mystery, one that challenges our very understanding of what a star is. Cosmic rays streak through the galaxy at nearly the speed of light, and they carry a secret that could rewrite our understanding of the interstellar medium. These are not rays of light but high-energy particles, mostly protons and atomic nuclei, that have been accelerated by supernova shock waves, pulsars, and other violent events. They zip through space, ionizing the gas they pass through, heating it, and driving chemical reactions that would otherwise be impossible. And yet, for all their importance, we are missing an entire population of them. The cosmic rays we detect on Earth are the high-energy ones, the particles that punch through our atmosphere and trigger the flashes in observatories like the Pierre Auger Observatory. But theory predicts there should be far more cosmic rays at lower energies, particles with energies below 1 billion electron volts that are far less energetic but far more numerous. These low-energy cosmic rays should dominate the ionization and heating of dense molecular clouds, the very places where stars and planets are born. But we can only guess at their numbers because our own sun gets in the way. The solar magnetic field and the solar wind sweep these low-energy particles away from Earth, a phenomenon called solar modulation. It acts like a cosmic ray filter, blocking the very particles we most need to study. For decades, all we have had are indirect clues. For example, the abundance of certain molecules like H3 plus in dense clouds can only be explained if there is a steady source of ionization. Cosmic rays are the only source that can penetrate deep into these dark, shielded regions. The observed levels of ionization imply a flux of low-energy cosmic rays that is higher than what we see at Earth, but exactly how much higher remains unknown. The mystery has profound consequences. If the low-energy cosmic rays are more abundant than we assume, they will heat the gas more, altering the balance between gravity and pressure that determines when a cloud collapses. They will also drive a rich chemistry, creating complex organic molecules on the surfaces of dust grains. If they are rarer, then star formation might proceed more slowly, and the chemical inventory of protoplanetary disks could look very different. We simply do not know which scenario is correct. Fortunately, the puzzle is finally being tackled. The Voyager spacecraft, now beyond the influence of the solar wind, have begun to measure cosmic rays directly in the interstellar medium. Their data hints at a higher low-energy flux than predicted. Meanwhile, new missions are being designed, like the proposed interstellar probe, which would travel even farther to sample pristine cosmic rays. And on Earth, radio astronomers are developing new techniques to detect the faint radio emission produced when low-energy cosmic rays interact with magnetic fields in clouds. These methods could finally map the invisible population. Until then, every model of star formation, every prediction about the chemistry of space, and every story we tell about the birth of planets rests on an assumption about these missing particles. Finding them is not just a technical challenge, it is the key to unlocking the hidden engine that drives the interstellar medium. A cold cloud sits just a few dozen light years from a bubble of gas heated to 1,000,000 degrees. Yet they coexist in the same galaxy, separated by nothing but a thin boundary that holds its shape for millions of years. This is possible because the interstellar medium is not a single, uniform substance. It exists in distinct phases, each with its own temperature and density, and each phase is maintained by a delicate balance between heating and cooling. The heating comes from several sources. Ultraviolet starlight strikes dust grains and knocks electrons loose, a process called photoelectric heating that warms the gas around it. Cosmic rays, those energetic particles we discussed, collide with atoms and transfer energy, adding heat even in the darkest clouds. And X-rays from supernova remnants and hot gas can penetrate deep into neutral regions, depositing energy along the way. But these mechanisms are not fully understood. For example, the efficiency of photoelectric heating depends on the size and composition of dust grains, which, as we saw, remain poorly characterized. The contribution of low-energy cosmic rays is also uncertain, and X-ray heating only works in the most energetic environments. Against this input, the gas must lose heat just as fast to remain stable. It does so primarily by emitting radiation. When an atom or molecule is excited by a collision, it can later release that energy as a photon, cooling the gas. The most important coolants in diffuse clouds are atomic hydrogen at its 21-centimeter line, carbon in its fine structure lines, and molecular species like carbon monoxide in denser regions. Each of these lines tells a story. By observing their strengths, astronomers can infer the temperature and density of the gas. But interpreting these signals is tricky because the emission can be blocked by dust or blended with other sources along the line of sight. Far-infrared observations from space telescopes like the Herschel Space Observatory and the Stratospheric Observatory for Infrared Astronomy, or SOFIA, have mapped these cooling lines across the galaxy. They show that the warm neutral medium at about 6,000 to 10,000 degrees is widely distributed, while the cold neutral medium at around 50 to 100 degrees is concentrated in thin sheets and filaments. Yet the exact balance between heating and cooling that maintains these two phases remains one of the great unsolved puzzles. The two-phase model, first proposed in the 1960s, predicts that the atomic medium should naturally separate into cold and warm components, but it requires a specific range of pressures and heating rates. Observations often find pressures that fall outside that range, suggesting that additional heating or cooling processes are at work. Perhaps magnetic fields suppress turbulence and alter the heating, or perhaps the gas is constantly stirred by supernova shocks, preventing it from ever reaching equilibrium. The plasma phase at millions of degrees adds another layer. It is so hot that it emits mostly in X-rays and cannot cool efficiently, which means it can persist for a long time. But how does it coexist with the cold clouds it surrounds? The boundary between them must be incredibly sharp, held in place by magnetic fields and the pressure of the hot gas itself. Yet we have very few direct measurements of those boundaries. The whole structure resembles a cosmic weather system, where heating and cooling act like the atmosphere's energy budget, determining whether clouds form or dissolve. And just as on Earth, small changes in that budget can shift the entire state of the system. Understanding this thermal balance is not only a fundamental problem in astrophysics. It dictates where stars can form, how long the gas remains in a diffuse state, and what kind of chemistry can happen. Without a firm grasp of these heating and cooling processes, our models of the interstellar medium remain built on shaky ground. The next time you see a dark nebula silhouetted against a starry background, you are looking at a place where this invisible war between energy gain and loss has reached a temporary truce. But the war never ends, and the outcome shapes the galaxy around us. Inside those cold, dark clouds, a silent chemical factory is running. The same regions where thermal balance holds its truce, where dust grains gather icy mantles and cosmic rays carve out a subtle glow, are also the places where the universe builds its most complex molecules. Astronomers have now detected over 200 different molecular species in the interstellar medium, including alcohols, acids, and even the simple sugar glycolaldehyde. Among the most tantalizing finds are molecules that resemble the building blocks of life as we know it, like amino acid precursors, which could, under the right conditions, assemble into proteins. Yet despite this rich catalog, the chemical pathways that create these complex species remain frustratingly unclear. The challenge lies in the environment itself. In the dense, cold cores of molecular clouds, temperatures hover around 10 degrees above absolute zero. At such temperatures, gas phase reactions, the kind that happen easily in a warm laboratory flask, are sluggish at best. Two atoms or small molecules might drift through the cloud for millions of years without ever colliding with enough energy to form a bond. So how do larger molecules actually grow? One key route is grain surface chemistry. Dust grains are not passive bystanders. Their surfaces act as tiny scaffolds where atoms and smaller molecules can land, stick, and diffuse across the icy mantle. When two reactants meet on that icy surface, they can react with much less energy than they would need in the gas phase. The ice itself becomes a reservoir. Water, carbon monoxide, carbon dioxide, methane, and ammonia freeze onto the grains in layers, and over time, ultraviolet light from nearby stars or from the diffuse interstellar radiation field penetrates these ices, breaking bonds and creating radicals. Those radicals can then combine, forming more complex organic molecules. Laboratory experiments that simulate these conditions have shown that irradiating simple ices with UV light produces a rich mixture of compounds, including amino acids after the sample is warmed. But the laboratory can only mimic a small slice of the full interstellar environment. The exact composition of the ice, the flux of UV photons, the temperature history, and the presence of cosmic rays all affect the final product. And we still do not know how efficiently these molecules are released back into the gas phase, where we can detect them by their rotational and vibrational signatures. Another important process is radiative association, particularly for building carbon chains and complex ions. In this mechanism, two atoms or molecules collide and form a temporary complex that can release the excess energy by emitting a photon, stabilizing the bond. This is extremely slow at low densities because the reactants rarely stay together long enough to radiate, but in the thin gas of some interstellar clouds, it remains one of the few ways to build certain species. The interplay between these pathways, gas phase, grain surface, and radiative association, creates a tangled web that models are only beginning to unravel. The astrobiological significance cannot be overstated. If the interstellar medium can produce the chemical precursors for life, then every new star and planetary system starts with a head start toward biological potential. The material that formed our own solar system likely contained a rich inventory of organic molecules delivered by comets and meteorites. Understanding exactly how those molecules formed in the interstellar medium is not just a puzzle for chemists. It is a link between the cold, dark clouds of the galaxy and the origin of life on a small rocky planet. As laboratory techniques improve and new telescopes like the James Webb Space Telescope peer into the infrared fingerprints of these ices, we are finally beginning to see the recipe book that the universe has been using for billions of years. But many of the pages are still missing, and each new discovery reveals just how much more there is to learn. The cold clouds where those molecules form are not randomly scattered. They are organized into vast sheets and filaments that stretch across hundreds of light years, but our maps of this structure are frustratingly incomplete. The cold neutral medium is the densest atomic phase of the interstellar medium, sitting at temperatures around 50 to 100 degrees, and it is the raw material that eventually gathers into molecular clouds and collapses into stars. Yet we cannot see its true shape because of two fundamental obstacles: opacity and resolution. At the 21-centimeter line of atomic hydrogen, the cold gas is optically thick. That means the emission we detect comes only from the frontmost layer of the cloud, like trying to measure the depth of a forest by counting the trees at the edge. Deeper structures remain hidden behind a wall of self-absorption. Absorption studies offer an alternative. When a bright background radio source shines through the cold gas, the atoms in the foreground leave a fingerprint by absorbing some of that light. This technique gives us a direct measurement of the gas column density along that single, narrow line of sight. But those lines of sight are like drinking straws poked through a sponge. We get exquisite detail in one dimension, but almost no information about the three-dimensional arrangement, and the cold gas is known to be structured on scales smaller than a parsec, tiny compared to the gaps between our lines of sight. So the vast majority of its clumps and filaments are simply missed. The problem is made worse by complex velocity structures. The cold neutral medium does not sit still. It moves with the turbulent churn of the galaxy, and different clouds along the same line of sight often have overlapping velocities. When we see a broad absorption feature, we cannot always tell if it comes from one thick cloud or many thin ones that happen to be moving at the same speed. This degeneracy hides the true number and distribution of the smallest clumps. Observers try to disentangle the velocities by looking at multiple spectral lines from different species, but the interpretation remains ambiguous. Some studies suggest the cold gas is organized into thin, fractal sheets that are only a few hundredths of a parsec thick, but we have no way to directly confirm that across large regions of the sky. This is not just a cartographic puzzle. The spatial distribution of the cold neutral medium directly controls how molecular clouds form and how stars are born. If the gas is concentrated into sharp, filamentary strands, then the process of turbulence and gravity that drives it toward collapse will behave very differently than if it is spread out in smooth, thick slabs. Numerical simulations that model star formation rely on initial conditions that describe this distribution. If those initial conditions are wrong, the entire cascade from diffuse atomic gas to dense stellar cores is misrepresented. The mystery reaches even larger scales. The arrangement of cold gas shapes the way the galaxy looks at radio wavelengths and influences how we interpret surveys of the Milky Way structure. Spiral arms, for example, are traced by atomic hydrogen, but the cold component of that hydrogen is precisely the part that gives us the sharpest contrast. Without a clear map, our picture of the galaxy's skeleton remains blurry. Researchers are now working on new techniques to overcome these limits. They use multiple background sources, such as pulsars and quasars, to create a sparse but three-dimensional network of absorption lines. They also combine the 21-centimeter emission data with absorption data to model the optical depth and recover the true column density. Machine learning algorithms are being trained on simulated data to infer the hidden clumps from the smeared observations. But for now, the cold neutral medium keeps much of its structure hidden. Every time we think we have a clear view of how the interstellar medium is organized, the fog of opacity and the limits of resolution remind us that we are only seeing the surface. And what lies beneath, the thin sheets and tiny clumps where stars may already be forming, remains a landscape we can only guess at. From the cold sheets of gas to the fiery explosions that drive them, the cycle continues upward. The interstellar medium is not a static reservoir. It is a dynamic system that exchanges matter with the galactic halo and beyond, a process astronomers call the galactic fountain. The idea is elegant. When massive stars end their lives as supernova, they release enormous amounts of energy and heavy elements into their surroundings. That energy heats the surrounding gas to millions of degrees, creating a hot, tenuous plasma that expands like a rising balloon. Because the gas is so hot, it is buoyant, and it rises out of the galactic disk into the halo, a region that stretches far above and below the plane of the Milky Way. There, the gas slowly cools by emitting X-rays. As it loses energy, it becomes denser and eventually collapses back toward the disk, raining down as neutral or even molecular clouds. This falling gas carries with it the metals forged in the interiors of stars, enriching new regions of the galaxy and providing fresh fuel for the next generation of star formation. The model has been supported by observations for decades. We see hot X-ray emitting gas in the halo, and we see neutral hydrogen clouds falling toward the disk at high velocities. Yet the details of this cycle remain frustratingly hazy. One of the biggest uncertainties is the rate at which gas actually moves through this loop. How much mass rises per supernova? How long does the cooling take? The answers depend on the density and magnetic field structure of the halo, which we have only mapped in the broadest strokes. The metals themselves add another layer of mystery. When a supernova explosion enriches the surrounding gas, those heavy elements are mixed into the hot phase. But as the gas rises and cools, some of those metals may condense onto dust grains, removing them from the gas cycle. How efficiently this happens and how it affects the chemical evolution of the galaxy over billions of years is still debated. If too many metals get locked into dust, the fountain becomes less effective at spreading them, and star-forming regions may become chemically distinct from one another. Observations of the circumgalactic medium, the diffuse halo of gas that surrounds the entire galaxy, are beginning to reveal the large-scale structure of this flow. Using the absorption lines of highly ionized atoms like oxygen 5 times or carbon 4 times, astronomers can trace the hot and warm phases of the fountain as they move through the halo. But these absorption measurements only give a snapshot along a single line of sight. To truly understand the three-dimensional flow, we need multi-wavelength surveys that track the gas in X-rays, ultraviolet, and radio simultaneously. Such surveys would allow us to measure the temperature, density, and velocity of the gas at different stages of its journey, from the bright, hot bubbles near supernova remnants to the diffuse, cooling clouds high above the disk. Without this kind of comprehensive view, the galactic fountain remains a beautiful theory with only patchy confirmation. And yet, the rising hot gas itself holds even deeper secrets. What happens to that million-degree plasma when it reaches the outer halo? Does it mix with the circumgalactic medium, or does it continue to expand into intergalactic space? The answers are waiting in the faint X-ray glow that astronomers are only now beginning to resolve. That rising million-degree plasma holds another mystery of its own. It is the hottest and most pervasive phase of the interstellar medium, the hot ionized medium, and it fills most of the volume in the galactic disk and halo. Yet for all its dominance, we know remarkably little about its true structure and behavior. The gas is so thin that a cubic centimeter of space, the volume of a sugar cube, might contain only a single charged particle. But that particle is moving with tremendous energy, having been kicked to millions of degrees by the shock waves from supernova explosions. When a massive star detonates, its blast wave expands outward at thousands of kilometers per second, sweeping up the surrounding gas and compressing it into a shell. Inside that shell, the temperature rises to 1,000,000 degrees or more, and the material becomes a tenuous X-ray emitting plasma. Over time, multiple supernova remnants overlap, their hot interiors merging to form a network of bubbles that permeates the galaxy. This is the hot ionized medium, and it is thought to be the dominant phase by volume. But the exact fraction of space it occupies, known as the filling factor, is still a matter of active debate. Some models suggest the hot phase covers more than half the volume of the galactic disk, while others put that number much lower, around a quarter or less. The uncertainty matters because the hot ionized medium plays a crucial role in regulating the interstellar medium as a whole. Its high pressure exerts a force on the surrounding cold and warm clouds, shaping their boundaries and influencing their collapse. It also provides a conduit for cosmic rays, guiding them out of the disk and into the halo along magnetic field lines. Yet the X-ray emission that reveals its presence is faint and smooth, making it hard to distinguish one hot bubble from another. The best maps come from the Chandra and XMM Newton observatories, which have surveyed the diffuse X-ray background across the sky. They show a soft glow that varies in intensity, but separating the foreground emission from the background signal from the distant galactic halo or even extragalactic sources is a delicate task. In some directions, the emission is so faint that it disappears into the noise. Another deep puzzle is the cooling time of this hot gas. At 1,000,000 degrees, the plasma loses energy by emitting X-rays, but because the density is so low, collisions between particles are rare and the cooling is extremely slow. A typical hot bubble might take tens of millions of years to radiate away its energy and drop back to lower temperatures. That is a long time compared to the rate at which new supernova inject energy, raising the question of whether the hot phase has ever reached a steady state. Perhaps it is constantly fluctuating, with some regions cooling and collapsing while others are freshly heated by new explosions. The structure of the hot ionized medium may not be uniform at all. Instead, it could be highly filamentary and porous like a sponge with dense knots and empty voids. This idea comes from simulations that show how multiple supernova remnants interact. When two bubbles overlap, their hot interiors merge, creating a larger, lower-density cavity. Meanwhile, the material swept up into the shells can become dense and cool, forming the boundaries that separate the hot regions from the warmer phases. The result is a chaotic, interconnected network where the hot gas is concentrated into channels and lobes rather than spread evenly. Recent observations of the galactic halo support this view. X-ray images show plumes and chimneys of hot gas rising above the plane, suggesting that the hot ionized medium is not a static blanket but a dynamic, outflowing wind. This wind may carry mass and metals out of the galaxy, linking the hot phase to the circumgalactic medium and beyond. The mystery of the hot ionized medium is thus tied to the larger puzzle of how energy flows through the interstellar medium. Supernova dump a huge amount of kinetic and thermal energy into the gas, but how much of that energy is radiated away, and how much is channeled into turbulence, magnetic fields, or cosmic rays remains unknown. The hot phase is the most direct tracer of that energy budget, and understanding its true structure and behavior is essential for closing the books on the galactic energy cycle. Until we can map the hot gas in 3 dimensions with enough sensitivity to see its internal structure, we will be left with only a ghostly outline of the most energetic component of the space between stars. The most energetic particles known to exist are racing through the interstellar medium right now, and their true origins remain one of astrophysics' greatest unsolved puzzles. These are very high-energy cosmic rays, particles that carry more than 1 billion times the energy of protons accelerated in the largest man-made colliders. Some of them pack 1,000 times more punch than that, and as they tear across the galaxy at nearly the speed of light, they leave behind a trail of gamma rays that traces their invisible highways through the interstellar medium. But the story of where these particles come from and how they get so energetic is not as simple as we once thought. For decades, the leading explanation has been supernova remnants. When a massive star explodes, it launches a blast wave that expands outward for thousands of years. That shock wave acts like a natural particle accelerator, bouncing charged particles back and forth across the magnetic field lines until they gain enormous energy. This process, known as diffusive shock acceleration, can boost protons and nuclei up to energies of about 1,000,000 billion electron volts, or 1 petelectron volt, a unit astronomers call a PV. That is the theoretical maximum for supernova remnants, and observations of gamma rays from some young remnants seem to confirm that these objects can indeed produce cosmic rays up to that limit. But here is where the mystery deepens. Beyond that energy, around what is called the knee in the cosmic ray spectrum, something changes. If you plot the number of cosmic rays detected at Earth against their energy, the curve drops steadily until it reaches about 3 PV. Then it takes a sudden steeper plunge, a break in the slope that astronomers have named the knee. This feature suggests that there is a fundamental limit to how fast the galaxy's own accelerators can push particles. Above that threshold, different sources must take over, likely objects outside the Milky Way altogether, like active galactic nuclei, gamma-ray bursts, or the shocks around massive galaxy clusters. But the exact transition point and the relative contribution of galactic versus extragalactic sources is still fiercely debated. The interstellar medium plays a crucial role in this drama. Cosmic rays do not travel in straight lines through empty space. They are constantly scattered by the magnetic fields that thread through the interstellar medium, causing them to diffuse like smoke spreading through a room. The density of gas and the strength of those magnetic fields determine how quickly cosmic rays escape the galaxy and how far they travel before colliding with something. When a high-energy cosmic ray does slam into a hydrogen atom or molecule in a cloud, it produces a spray of secondary particles, including neutral pions that quickly decay into gamma rays. Those gamma rays are our most direct tracer of where cosmic rays are being accelerated and how they propagate. Thanks to observatories like the Fermi Gamma Ray Space Telescope and ground-based arrays like the High-Energy Stereoscopic System, or HESS, astronomers have mapped gamma-ray emission across the galaxy. The closest regions to supernova remnants glow brightly, showing that cosmic rays are freshly accelerated there. But farther away, the gamma-ray glow becomes more diffuse, reflecting the steady sea of older cosmic rays that have spread throughout the interstellar medium. The amount of gamma-ray emission depends on how much gas is available to collide with, which means the structure of the interstellar medium itself, its clumps, voids, and filaments, directly imprints onto the gamma-ray map. This leads to a deep puzzle. Models of cosmic ray propagation rely on assumptions about the spatial distribution of interstellar gas and magnetic fields. If those assumptions are wrong, our estimates of how quickly cosmic rays escape the galaxy and how many of them come from extragalactic sources could be off by a factor of 2 or more. For instance, some observations suggest that cosmic rays may travel much farther through the halo than previously thought, implying a more porous medium with weaker magnetic fields. Others indicate that the diffusion is slower, trapping cosmic rays near their birthplaces for tens of millions of years. Reconciling these conflicting signals requires a much finer understanding of the interstellar medium's structure across all scales. The NE itself may actually be telling us something about the interstellar medium's role in shaping the cosmic ray spectrum. Some models propose that the break is not caused by a limit on the accelerators, but by the way cosmic rays lose energy as they pass through the galaxy's magnetic fields and gas. Higher energy particles can escape more easily, so their numbers drop off faster. This idea, known as the propagation NE, would shift the responsibility from the sources to the medium itself. But proving it requires separating the effects of source physics from propagation physics, an extremely difficult task when we can only observe the final mixed result at Earth. New experiments like the upcoming Cherenkov telescope array and the space-based probe known as the Payload for Antimatter Matter Exploration and Light Nuclei Astrophysics, or PAMELA successor, are designed to measure cosmic ray composition and spectra with unprecedented precision. Combined with ever-sharper gamma-ray maps, these observations will finally test whether the NE is a signature of dying supernova remnants or a property of the interstellar medium. Until then, every flash of gamma light from a distant cloud is a clue, and every gap in our maps of the interstellar medium is a missing piece in the puzzle of where the most violent particles in the galaxy truly come from. A pulsar's signal flickers like a star seen through rippling water, but the cause is invisible electrons spread across light years. This phenomenon is called interstellar scintillation, and it happens because radio waves from pulsars and distant quasars are bent and scattered by free electrons in the interstellar medium. The resulting twinkle is not random. It carries a hidden map of the ionized gas that lies between us and those cosmic beacons. By studying how the signal wavers in brightness and position, astronomers can probe the structure of these electron clouds with a resolution far finer than any telescope could achieve directly. But that promise comes with a deep puzzle. The scintillation patterns reveal that the free electrons are organized into structures on scales as small as a few thousand kilometers, even though they are spread across many light years of space. Such tiny features demand steep density gradients, meaning the electron density changes dramatically over a short distance. That is hard to explain with standard models of interstellar turbulence, which predict that energy should cascade smoothly from large scales to small ones, leaving a relatively uniform distribution. Instead, the observations suggest something sharper, like blades of electron density slicing through the gas. The mystery matters because these same fluctuations in electron density distort the apparent positions of radio sources. When astronomers try to measure the precise location of a pulsar or a quasar, the scattering shifts the signal by tiny but detectable angles. This introduces errors in astrometry, the science of measuring cosmic positions and distances. For projects that rely on extreme precision, like tracking the orbits of stars near the supermassive black hole at the center of our galaxy or testing theories of gravity with pulsar timing, the uncertainty from interstellar scintillation can be the biggest source of noise. If the small-scale structure is discrete clouds, then the errors might be intermittent and localized. If it is part of a continuous turbulent cascade, then the errors would be more systematic and widespread. The two scenarios lead to very different strategies for correcting the data. So which is it? The debate has been running for decades. One camp proposes that the electron density irregularities come from discrete, isolated clouds, perhaps the shocked boundaries of old supernova remnants or the edges of ionized bubbles around hot stars. In this picture, each cloud acts like a lens that distorts the radio waves passing through it. The tiny scales we see are simply the size of those clouds. The other camp argues for a continuous field of turbulence, where the energy from large-scale motions, like the shear from galactic rotation or the blast waves of supernova, cascades down through smaller and smaller eddies until it reaches the scales we observe. In this view, the steep gradients are a natural result of compressible magnetohydrodynamic turbulence, which can create filaments and sheets of enhanced density. Observations have not settled the dispute. Sometimes the scintillation seems to come from a single dominant scattering screen, which supports the discrete cloud idea. Other times, the patterns are more complex, with multiple screens or a smooth distribution favoring turbulence. There are also hints that the properties of the electron density structure change with location in the galaxy, being different in the inner disk, the outer disk, and the halo. New surveys using arrays like the Very Large Array and the upcoming Square Kilometre Array are mapping scintillation across thousands of lines of sight. By correlating the patterns with known supernova remnants, H-Roman II regions, and other structures, astronomers hope to distinguish between the models. Until then, every flickering pulse from a pulsar is a tiny experiment in the physics of ionized gas, and every misaligned quasar position is a reminder that the space between the stars is not empty at all. It is filled with invisible, roiling, and finely structured plasma that constantly bends our view of the cosmos. Water is the most abundant molecule in the universe after hydrogen, yet its true distribution across the interstellar medium remains a stubborn puzzle. Astronomers have long known that water exists in two main forms out there, as a gas in diffuse and translucent clouds, and as a solid ice coating on dust grains inside dense, cold regions. But when they try to add up exactly how much water there should be, the numbers do not match. The total abundance of water vapor and ice, and the way that abundance shifts from one galactic environment to another, is far more variable and uncertain than simple chemical models predict. This is the mystery of the wet interstellar medium. One of the biggest surprises came from the Herschel Space Observatory, which operated from 2009 to 2013 and was specifically designed to see the far infrared and submillimeter light that water molecules emit. Herschel mapped water vapor across the Milky Way and found it in places where theory said it should be scarce, like in the tenuous gas of the diffuse interstellar medium. In those thin clouds, water should be quickly destroyed by ultraviolet light, broken apart into hydrogen and oxygen atoms, yet Herschel detected its spectral lines almost everywhere it looked. Something must be constantly reforming water in those regions, faster than the destruction can remove it. The leading explanation involves a series of neutral-neutral reactions starting with oxygen atoms and hydrogen molecules, but the rates required for that chemistry are higher than laboratory measurements suggest. So there is a fundamental discrepancy between the predicted and observed amounts of water vapor in the diffuse medium. Meanwhile, in the denser molecular clouds where new stars are born, water ice becomes the dominant reservoir. Observations of infrared absorption features toward young stellar objects show that the icy mantles on dust grains contain large amounts of water, often mixed with carbon monoxide, carbon dioxide, and methanol. But the relative abundance of water ice compared to the total amount of water locked in gas phase is not constant. Some clouds have much less ice than others, and the reason is unclear. It might depend on the history of the cloud, how many times it has been shocked by outflows from forming stars, or how much ultraviolet radiation has seeped into its edges. The spatial variation of water from diffuse vapor to dense ice is so patchy that it challenges our ability to build a simple picture of the water cycle in the galaxy. This matters because water is not just a passive ingredient. It is one of the most important coolants in the interstellar medium. When a water molecule rotates or vibrates, it can release energy in the form of infrared or submillimeter photons. That radiation carries heat away from the gas, allowing it to cool and collapse under gravity. In dense regions where other coolants like carbon monoxide become optically thick, water can take over and provide the final push toward star formation. Without a reliable inventory of where water is and how much there is, models of cloud collapse and star formation remain uncertain by a factor that could determine whether a cloud births a solar system or drifts apart. The Herschel results also revealed another layer of the puzzle: water mazes. In some regions, the water vapor is so densely packed and moving with just the right velocities that it amplifies radio emission in a natural laser-like process, creating bright, compact spots that can be tracked with great precision. These mazes act as beacons, revealing the motion and structure of gas in the innermost parts of star-forming regions and around dying stars. But why only some clouds produce mazes while others with seemingly similar conditions do not is not well understood. The presence of a maser seems to require a very specific temperature, density, and velocity field, and the probability of those conditions aligning is low. So the masers themselves are both a powerful tool and a statistical mystery. Every time we think we have a handle on the water budget in space, a new observation shows us just how much we are missing. The distribution of water vapor and ice across different phases of the interstellar medium is a tapestry we are still learning to read, and each thread pulls in a slightly different direction. Until we can trace the full cycle of water from diffuse atomic clouds to dense icy mantles and back into gas, the simple word what will remain a tantalizing label rather than a well-understood state. And that uncertainty echoes through every model of star formation, every estimate of the chemistry that may seed life, and every story we tell about the universe's most familiar molecule. The space between stars hides something even more elusive than hidden water reservoirs or missing baryons. It holds a shadowy component that does not emit, absorb, or reflect any light, yet its gravitational pull shapes the entire galaxy. Dark matter. For decades, astronomers have mapped its presence on the largest scales, in the rotation curves of galaxies and the bending of light around clusters. But a quieter, more perplexing question has emerged. Does dark matter also thread through the interstellar medium itself? Could some of the unseen mass that lurks within our own galaxy actually be hiding inside the very clouds where stars are born? The idea is deeply speculative, but it springs from a real tension in observations. When scientists calculate the total mass of a typical molecular cloud using its emitted radiation from carbon monoxide or dust, they get one number. When they measure the gravitational influence of that same cloud on nearby stars or on the motion of gas around it, they sometimes get a slightly different number. The discrepancy is small and often attributed to uncertainties in distance, temperature, or the conversion from carbon monoxide to total mass. Yet a persistent minority of studies hint that something extra might be there, a gravitational tug that cannot be accounted for by the visible gas and dust alone. That extra pull could be a sign of a dense clump of dark matter sitting right inside the cloud, or perhaps a diffuse halo of dark matter that envelops the cloud and helps hold it together against its own internal pressure. This is not as far-fetched as it sounds. Dark matter is thought to be distributed in a smooth, extended halo around the Milky Way, with density highest toward the center and tapering off outward. But within that smooth distribution, there could be smaller clumps, subhalos, that survived from the early universe and now drift through the galactic disk. If one of these clumps passed through a molecular cloud, its gravity would compress the gas, possibly triggering star formation or, conversely, stirring the cloud and preventing collapse. The cloud itself could also have formed within a region where dark matter density is unusually high, effectively becoming a nest for a hidden mass component. In either scenario, the cloud kinematics, the way its gas moves and rotates, would carry the signature of that extra gravity. How could we ever test such a speculative idea? One promising method is gravitational lensing. If a dense, compact clump of dark matter lies in front of a distant star or background galaxy, its gravity will bend the light, causing a brief, characteristic brightening known as microlensing. Surveys like the Optical Gravitational Lensing Experiment, or OGLE, have detected thousands of such events, most attributed to ordinary stars or brown dwarfs. But a tiny fraction of microlensing events have durations and brightness patterns that do not match any known stellar object. Those anomalies could be due to dark matter, clumps the size of a small planet or even smaller, drifting through the interstellar medium. So far, the numbers are too small to be certain, but future surveys with higher cadence and sensitivity may soon settle the question. Another test comes from the internal motions of the clouds themselves. In a cloud supported only by gas pressure and magnetic fields, the random velocities of its molecules should follow a predictable distribution. If an additional gravitational component from dark matter is present, those velocities would be subtly different, more like the motions of stars in a dwarf galaxy. By mapping the line of sight velocities across a cloud using spectral lines of carbon monoxide or ammonia, astronomers can look for a gravitational flaw, a minimum level of motion that cannot be explained by turbulence or rotation. Some clouds, especially the largest and most massive ones, show hints of such a flaw. But again, the signal is weak and could be caused by other factors, such as unresolved substructure or the influence of external tidal forces. The broader mystery here goes far beyond individual clouds. It touches on the fundamental nature of dark matter itself. If dark matter interacts with ordinary matter through gravity alone, then it should pass through the interstellar medium almost without a trace. But if it has even the faintest non-gravitational interaction, a tiny scattering cross-section with protons or electrons, then it could heat the gas, alter its chemistry, or even clump together in ways that leave visible imprints. The interstellar medium is in effect a natural detector for the particle physics of dark matter. Every cloud, every diffuse filament, every wisp of atomic hydrogen is a potential laboratory where the unseen could reveal itself. The challenge is that the signals are subtle and easily confused with ordinary astrophysical processes. But as our instruments grow sharper and our models more detailed, the space between stars may finally give up the secret of what most of the matter in the universe actually is. And that secret, if it ever comes, will change everything we think we know about the dark scaffolding that holds the cosmos together. The sun sits inside a giant bubble of hot gas. This void, stretching at least 300 light-years across, is known as the local bubble. It is a region where the interstellar medium is 1,000 times thinner than the average, a tenuous sea of million-degree plasma that surrounds our solar system and the nearest stars. But how did this enormous cavity form, and why does it still exist after millions of years? The leading explanation points to a series of supernova explosions. Over the past 10 to 15 million years, a cluster of massive stars in the Scorpius-Centaurus association blew up one after another, their shock waves sweeping the surrounding gas outward and leaving behind a hot, low-density emptiness. That emptiness is the local bubble. The boundaries of this cavity are not smooth walls. They are a tangle of neutral clouds, dense filaments of hydrogen that were compressed and sculpted by the advancing shock fronts. Some of these clouds, like the one that gave birth to the star-forming region in the constellation Taurus, lie right on the edge of the bubble. Others drift inside its interior, remnants of gas that somehow survived the violent clearing. The exact shape of the local bubble is still debated. Early maps based on the absorption of starlight by intervening gas suggested a roughly spherical cavity, but newer data from the Gaia spacecraft, which measures distances to stars with astonishing precision, reveals a far more irregular outline. The bubble appears to be elongated, with fingers and tunnels extending into the surrounding medium. One such tunnel may connect the local bubble to another cavity, the Loop I superbubble, which surrounds the Scorpius-Centaurus association. If confirmed, this would show that the interstellar medium is not a collection of isolated bubbles but a connected network of cavities and channels, like the pores of a sponge. Understanding the evolution of the local bubble is not just an exercise in cartography. It directly affects our own environment. The bubble's hot interior exerts a pressure on the heliosphere, the magnetic bubble that the sun inflates around itself with the solar wind. The heliosphere is our first line of defense against galactic cosmic rays, and its shape and size depend on the density and pressure of the interstellar medium outside. If the local bubble changes over time, perhaps because fresh supernovae go off nearby, the heliosphere could shrink or expand, altering the flux of energetic particles that reach Earth. This could have subtle influences on our atmosphere and even on climate over geological timescales. The local bubble also serves as a unique laboratory. Because it is so close, we can study its properties in exquisite detail with instruments that would struggle to resolve similar structures in distant parts of the galaxy. X-ray observatories like Chandra and XMM Newton have mapped the soft X-ray glow from the hot gas within the bubble. Ultraviolet telescopes have detected absorption lines from highly ionized atoms in its walls. Radio telescopes have traced the neutral hydrogen clouds that surround it. Each dataset adds another piece to the puzzle, yet fundamental questions remain unanswered. Is the bubble still expanding, or has it stalled and begun to cool? How many supernovae were required to carve it out? And what will happen when the current generation of nearby massive stars, like the blue supergiant in the Orion Nebula, eventually detonate? The local bubble is not a relic of the distant past. It is an active, dynamic structure that interacts with the interstellar medium in real time. By watching it evolve, we learn how the space around any star is shaped by the violent history of its neighbors. And because we are inside it, the local bubble is the one place where we can test our models of the interstellar medium with direct in situ measurements. Every new observation brings us closer to understanding the forces that sculpt our galactic neighborhood, and every unanswered question reminds us that even the space just outside our door still holds secrets waiting to be revealed. Our sun carves its own bubble within the local bubble's hot gas. This bubble is the heliosphere, a vast magnetic shield inflated by the solar wind, a constant stream of charged particles flowing outward from our star at hundreds of kilometers per second. The heliosphere pushes against the surrounding interstellar medium, deflecting most of the galactic cosmic rays that would otherwise rain down on Earth. Without it, the surface of our planet would be bathed in far more high-energy radiation, altering our atmosphere and potentially life itself. But the heliosphere is not a static, perfect sphere. Its shape and size depend directly on the properties of the local interstellar medium, the very same gas and dust we have been exploring. The density, temperature, and magnetic field strength of the cloud the Sun is currently moving through all act as external forces that compress or stretch the heliosphere like a balloon pressed by unseen hands. For decades, the only clues about this interaction came from indirect measurements and models. Then the Voyager spacecraft, launched in the 1970s, crossed the heliopause, the outermost boundary where the solar wind meets the interstellar medium, and sent back data that upended many assumptions. They found the outer heliosheath, the region just inside the boundary, to be far more turbulent than predicted. The magnetic fields there were tangled and intense, not the smooth, gently draped fields theorists had expected. The interstellar medium itself turned out to be denser and warmer in that direction, compressing the heliosphere on one side and stretching it on the other. Voyager also measured a surprisingly strong interstellar magnetic field, strong enough to influence the shape of the entire bubble. These revelations have transformed our picture of the Sun's immediate neighborhood from a calm, isolated cocoon into a dynamic, interacting system. The deepest mystery now is how the local interstellar medium changes over time. The Sun is not stationary. It orbits the galactic center, moving through different patches of the interstellar medium, each with its own density, temperature, and magnetic field. Some patches may be thin and hot, like the interior of the local bubble, while others are denser and colder, like the edges of a molecular cloud. As the Sun passes through these varying environments over millions of years, the heliosphere expands and contracts. Its protective capacity waxes and wanes. At times, it may shrink enough to let far more cosmic rays into the inner solar system, with potential consequences for Earth's climate and the long-term stability of our biosphere. We have only glimpsed the present state of the local interstellar medium from the two tiny windows of Voyager 1 and Voyager 2. Their measurements are invaluable but limited to 2 lines of sight. We do not yet know the three-dimensional structure of the cloud we are currently embedded in, nor how it connects to the larger magnetic fields and turbulence of the local bubble. New missions, like the proposed interstellar probe, aim to travel much farther and sample the pristine interstellar medium directly, mapping its properties across a wider region. Until then, the shape of the bubble we live in, and the cosmic weather it protects us from, remains partly a mystery written in the invisible gas just beyond the reach of our senses. Every new data point from Voyager or from future spacecraft will refine our understanding of how our star interacts with the space around it, reminding us that even the nearest interstellar medium is a foreign, active environment that holds sway over our own world. Dust grains face a hostile universe inside every supernova shock. When a massive star explodes, its blast wave rips through the surrounding gas at thousands of kilometers per second. The dust grains caught in that shock are pelted by fast-moving atoms and ions, a process called sputtering that chips away at their surfaces molecule by molecule. In the hot million-degree plasma that fills supernova remnants, even the toughest silicate and carbon grains can be completely destroyed within a few thousand years. And yet, despite this constant assault, the Milky Way is filled with dust. Something must be rebuilding these tiny particles just as fast as they are torn apart. The leading explanation is that dust grains grow inside the dense, cold clouds where stars are about to be born. In these regions, atoms and molecules that were once in the gas phase stick to the surfaces of existing grains, a process known as accretion. The grains also collide with one another and stick together through a process called coagulation, building up larger and more complex particles. Both mechanisms are efficient only in environments where the density is high enough for frequent collisions, and where the temperature is low enough that the grains can hold onto their newly acquired material. That is exactly the kind of environment found in the heart of a molecular cloud, where the gas is 100 to 1,000 times denser than the average interstellar medium. But the balance between destruction and growth is incredibly delicate. If destruction were even slightly more efficient, the galaxy would quickly run out of dust. Star formation would become less efficient because the gas would lack a key coolant and catalyst, and the universe would look very different. If growth were more efficient, dust grains would become too large, altering how they scatter and absorb starlight, and potentially choking off the formation of planetary systems. Observations suggest that the two processes are roughly in equilibrium, but the exact rates remain uncertain by a factor of 2 or more. One of the best ways to measure this balance is to study the depletion patterns of elements in the interstellar gas. When an element like silicon or iron is locked up in dust grains, it disappears from the gas phase. Astronomers can measure the abundance of these elements in the diffuse interstellar medium and compare it to the cosmic average. The missing fraction tells them how much of that element has been incorporated into grains. These depletion studies show that some elements are heavily depleted in dense clouds, indicating active grain growth, while in the diffuse medium, the depletion is lower, suggesting that shocks have destroyed a significant portion of the dust. By mapping these patterns across different regions of the galaxy, scientists can infer where destruction dominates and where growth takes over. Another powerful clue comes from infrared emission. Warm dust grains glow at mid-infrared wavelengths, and the shape of that glow reveals grain size and composition. The Spitzer Space Telescope and the James Webb Space Telescope have observed this emission across star-forming regions, showing that the smallest grains are often missing near hot stars, destroyed by the intense radiation, while larger grains accumulate in the dense filaments that are about to collapse. This spatial variation provides a snapshot of the ongoing battle between creation and destruction. The implications of this cycle reach far beyond dust itself. The grains that survive in the interstellar medium are the seeds of planet formation. They clump together in protoplanetary disks, growing into pebbles, boulders, and eventually planets. If the balance of destruction and growth were different, the starting materials available to newborn solar systems would be altered, potentially changing the kinds of planets that can form. Earth itself is built from the remains of countless interstellar dust grains that survived billions of years of supernova shocks and gentle accretion in dark clouds. Every time a new star lights up, it inherits a legacy written in the dust that came before. And every time a supernova erupts, it sends a wave of destruction through that same dust, ensuring that the cycle of birth and death continues. Understanding exactly how that cycle works and how the numbers add up across the galaxy is one of the final pieces in the puzzle of how a cloud of gas and dust transforms into a world like our own. Galaxies are stunningly inefficient at turning gas into stars. If you took a typical molecular cloud and let gravity pull it inward without any interference, all of its material would collapse into stars in just a few million years, far less time than the age of the galaxy itself. Yet observations show that the Milky Way forms only about one new sun per year on average. The same inefficiency holds for nearly every galaxy we have measured. This profound mismatch between the speed of free fall and the actual pace of star birth is one of the central puzzles of the interstellar medium. The missing piece is a collection of forces that hold the gas up, preventing it from collapsing all at once. Turbulence creates chaotic motions that stir the cloud like a cosmic blender, resisting the inward pull of gravity. Magnetic fields thread through the gas and provide additional pressure, acting as a spring that pushes back against compression. And then there is feedback, the energy released by newly formed stars in the form of radiation, winds, and supernova explosions that heats and disperses the surrounding gas, shutting off further star formation before it can consume the entire cloud. The question is which of these processes dominates and how they work together across different scales ranging from a single dense core to an entire galaxy. Astronomers try to answer this by studying a fundamental relationship known as the Kennicutt-Schmidt law. When you plot the density of gas in a galaxy against the rate at which that galaxy forms stars, a clear pattern emerges. The star formation rate increases roughly as the gas density raised to a power of about 1.4. This simple power law holds across a wide range of galaxy types from spirals to starbursts, and it suggests that the physics of star formation is universal. But the scatter around that line is huge. Two galaxies with the same gas density can have star formation rates that differ by a factor of 10. Something else is controlling the efficiency, and that something is tied to the structure and dynamics of the interstellar medium. In some galaxies, the gas might be highly turbulent, stirred by the violent energy of many supernovae, which keeps it diffuse and resistant to collapse. In others, a strong magnetic field might suppress the gravitational fragmentation that leads to stars. And in still others, the feedback from massive stars might be so intense that it blows the gas out of the galaxy entirely, halting star formation for tens of millions of years. The scatter is not noise, it is a signal. It tells us that the efficiency of star formation is not a fixed number but a variable that depends on the local conditions of the interstellar medium, the very medium we have been unraveling. To understand which factor matters most, astronomers turn to simulations that model the full complexity of the gas, including turbulence, magnetic fields, and feedback. These simulations reproduce the Kennicutt-Schmidt relation reasonably well, but they also show that the relative importance of each process shifts with the environment. In a dense, metal-rich cloud, cooling may be so efficient that magnetic fields cannot hold it up, and turbulence becomes the main brake. In a diffuse, low metallicity region, magnetic fields might dominate. The interstellar medium is not a uniform ingredient. It is a living, breathing system where the balance of forces changes from one star-forming region to the next. This brings us directly to the next mystery. Among all the forms of feedback, those from the most massive stars are the most powerful and the most destructive. When a star more than 10 times the mass of the Sun ignites, it unleashes intense ultraviolet radiation that carves out vast ionized bubbles in the surrounding gas. Its stellar wind blasts away material at supersonic speeds, and when it dies in a supernova, it injects a shock wave that can trigger or quench star formation in the surrounding cloud. Understanding exactly how this feedback couples with the interstellar medium, and whether it ultimately enhances or suppresses star formation on a galactic scale, is one of the deepest unsolved problems in astrophysics. The answer will determine not only how galaxies build their stars, but how the cosmic cycle of gas and dust, the same cycle that built our own solar system, continues across the universe. Massive stars are the galaxy's most violent engines. When one of these behemoths ignites, it does not simply sit quietly and shine. It unleashes a barrage of energy that ripples through the surrounding interstellar medium for millions of years. Stellar winds, streams of charged particles blasting outward at thousands of kilometers per second, carve cavities into the gas. Ultraviolet radiation, intense enough to strip electrons from hydrogen atoms, ionizes vast bubbles around the star. And when that star eventually exhausts its fuel and collapses, the resulting supernova injects an explosive shock wave that can travel for hundreds of light years, compressing and heating everything in its path. Together, these three forms of feedback, winds, radiation, and supernova, are the primary way that massive stars communicate with their environment. They sculpt the density structure of the interstellar medium, drive the turbulence that stirs the gas, and determine whether nearby clouds will collapse into new stars or be torn apart. But here is the heart of the mystery. When astronomers run computer simulations that include all these processes, the results rarely match what telescopes actually see. The simulated clouds often lie much longer or shorter than they should. The bubbles and filaments appear too smooth or too chaotic. The star formation rates come out wrong. Something fundamental is missing from our models, and that missing piece may be the feedback itself. One of the biggest uncertainties is the efficiency of that feedback. How much of the energy and momentum from a massive star actually couples to the surrounding gas, and how much simply escapes into the void? Theoretical estimates suggest that only a small fraction, perhaps just 1% of the energy from a supernova, goes into stirring the interstellar medium. The rest radiates away, but that tiny fraction is still enormous, enough to disrupt a whole molecular cloud. The problem is that we do not know where that 1% goes or how it spreads through the gas. Different models make wildly different predictions. Some assume that feedback is catastrophic, meaning it rapidly blows apart the parent cloud and shuts down star formation almost completely. Others favor a gentler, more gradual process where feedback slowly erodes the cloud over millions of years, allowing many generations of stars to form before the gas finally disperses. The truth likely lies somewhere in between, but pinpointing it requires a detailed understanding of how the energy from a single supernova propagates through a turbulent, magnetized medium. That is an incredibly difficult calculation, and every simplifying assumption we make introduces error. Observations add another layer of confusion. When we look at real star-forming regions, we see that the clouds around young massive stars often survive for tens of millions of years, even after multiple supernovae have gone off inside them. That suggests feedback is not as destructive as the catastrophic models claim. Yet in other regions, like the giant molecular cloud that gave birth to the Orion Nebula, the gas is being blown away at hundreds of kilometers per second, revealing that feedback can indeed be violent. The variation from cloud to cloud is enormous, and we do not yet have a framework to predict which outcome will occur. This is not just an academic puzzle. The feedback loop between massive stars and the interstellar medium controls the rate at which galaxies build their stellar populations. If feedback is gentle, galaxies form stars more efficiently and grow faster. If it is catastrophic, star formation is stifled, and galaxies remain smaller and less bright. The balance between these two extremes shapes the entire history of the universe, from the first galaxies to the Milky Way and beyond. And right now, we are stuck. Our simulations cannot reproduce the full range of observed structures, and our theoretical models cannot agree on a single mechanism. The answer may lie in the tiny details, in the way a shock wave interacts with a magnetic field line, or in the precise spectrum of the radiation that heats the gas. Every new observation from facilities like the James Webb Space Telescope and the Atacama Large Millimeter Array is another clue, but the puzzle remains far from solved. Until we understand how massive stars really talk to the space around them, we are only guessing at the engine that drives the cosmic cycle of birth and death. The clouds that feed that engine are hiding their true shape. When astronomers point a telescope at a molecular cloud, what they see is a flat projection, a two-dimensional shadow of a three-dimensional object. The image shows how much gas and dust lie along the line of sight, but it reveals nothing about how that material is distributed in depth. Is the cloud a thin sheet seen face-on or a long filament seen end-on? Is it a dense, compact sphere or a loose, puffy collection of clumps? Without that depth information, our picture of these stellar nurseries is like looking at a city skyline from a distance. You see the silhouette, but you miss the streets and alleys and hidden courtyards that shape the city's life. Gravity, however, does not work in two dimensions. The way a cloud collapses to form stars depends critically on its true three-dimensional shape. A flattened sheet will fragment differently than a long, narrow filament. A dense spherical core will collapse much faster than a diffuse, irregular clump of the same mass. For decades, astronomers had to rely on statistical methods to infer these shapes. They would measure the projected shapes of many clouds and assume they were randomly oriented in space, then average the results to get a typical three-dimensional form. This approach worked well enough for broad surveys, but it could not tell us the actual structure of any single cloud, and it missed a crucial fact: clouds are not all alike. The interstellar medium is a patchwork of different environments, and each cloud carries the signature of its own unique history of turbulence, magnetic fields, and feedback. Recently, two new techniques have begun to peel away the mask. The first is chemical modeling. Different molecules form at different depths within a cloud because ultraviolet light from nearby stars penetrates only the outer layers. Deep inside, the chemistry is driven by cosmic rays and grain surface reactions. By mapping the relative abundances of molecules like carbon monoxide, which is bright everywhere, and diazonilium, which only exists in the densest, most shielded interiors, astronomers can trace the cloud's internal structure layer by layer. It is like using a set of chemical flashlights to illuminate the hidden shelves and caverns within a vast, dark warehouse. The second technique is kinematic modeling. The gas inside a cloud is never still. It moves under the influence of turbulence, gravity, and external shocks, and those motions produce Doppler shifts in the spectral lines. By measuring how the velocity of a particular molecule changes from one point on the sky to the next, scientists can reconstruct the three-dimensional flow pattern of the gas. This is analogous to using the sound of a passing train to deduce its shape and speed, but applied across an entire cloud. The most powerful breakthrough, however, has come from the Gaia spacecraft. Gaia measures the distances to billions of stars with extraordinary precision, and by combining those distances with maps of how starlight is dimmed by interstellar dust, astronomers can now build three-dimensional maps of dust density across the entire Milky Way. These maps are transforming our view of molecular clouds. They reveal that clouds are not simple, smooth blobs. They are twisted, filamentary structures with voids and dense knots and long, thin tendrils that stretch for tens of light years. The topology is complex, like a deep sea sponge, with channels and cavities carved by the winds and radiation of massive stars. The implications for star formation are profound. A filament that is only a few tenths of a parsec wide can collapse under its own gravity much faster than a spherical cloud of the same mass, because the gas is already concentrated in a narrow line. The internal density variations, the hidden voids and compact clumps, determine exactly where the first stars will ignite and how many of them will form. Our models of star formation have long assumed that clouds are roughly spherical or at least well mixed, but the three-dimensional maps are showing us that this assumption is often wrong. Every new dataset from Gaia and from molecular line surveys reveals another layer of complexity that our simulations must capture. The true shape of the interstellar medium, the way it is folded and sculpted over thousands of light years, is still being unraveled. And until we can see those hidden dimensions clearly, our predictions for how stars are born, how they shape their surroundings, and how the cosmic cycle of gas and dust continues will remain tied to a flat and incomplete picture. The space between stars is not a flat canvas. It is a deep, twisting landscape, and we are only beginning to explore its secret contours. Every new star that ignites is a factory for heavy elements. Inside its core, hydrogen fuses into helium, then helium into carbon and oxygen, and onward up the periodic table until iron is reached. When that star ends its life, either by casting off its outer layers in a gentle planetary nebula or by exploding as a supernova, those freshly forged metals are scattered into the surrounding gas. Over billions of years, this process slowly enriches the interstellar medium, turning a primordial soup of hydrogen and helium into the chemically complex mixture we see today. The story of that enrichment, the chemical evolution of the interstellar medium across cosmic time, is one of the deepest puzzles in galaxy formation. We know the broad strokes. The universe began with almost no metals, only hydrogen and helium left from the Big Bang. The first stars, called Population 3, formed from that pristine gas and produced the earliest heavy elements. When they exploded, they seeded the surrounding medium with carbon, oxygen, silicon, iron, and everything else. Each subsequent generation of stars added more metals, and the average metallicity of the interstellar medium rose steadily. But when we try to pin down the exact timescales and the efficiency of mixing, we run into serious trouble. One of the biggest surprises came from observations of very distant galaxies, seen when the universe was only a few billion years old. Those galaxies, observed at high redshift, often show surprisingly high levels of metallicity. Their gas is already rich in heavy elements comparable to what we see in the Milky Way today. This is hard to explain because those galaxies should not have had enough time to form many generations of stars. The standard model predicts that enrichment takes several billion years to reach such levels, yet there they are, already chemically mature in the early universe. Something must be speeding up the process. Perhaps the earliest stars were more massive than we assume, producing metals faster and in greater quantities. Or perhaps the mixing of those metals into the interstellar medium was far more efficient, spreading the newly forged elements across vast regions in just a few 100 million years. We simply do not know which mechanism is at work. The challenge is partly observational. To measure the metallicity of a distant galaxy, astronomers look at the emission lines from its gas. Certain lines, like those from doubly ionized oxygen, are bright and easy to detect, but their strength depends not only on the abundance of oxygen, but also on the temperature and density of the gas. If those conditions are different from what we assume, we could be overestimating or underestimating the true metal content. Recent studies using the James Webb Space Telescope have begun to refine these measurements by observing multiple diagnostic lines simultaneously, but the uncertainties remain large. Even the local universe holds mysteries. Within the Milky Way, the chemical composition of the interstellar medium is not uniform. Different regions have different abundances of elements like carbon, nitrogen, and oxygen. The Galactic Center is metal-rich while the outer disk is more pristine. This gradient suggests that enrichment happens locally in star-forming complexes and then spreads slowly outward. But the efficiency of that spreading, how far and how fast metals diffuse through the turbulent, magnetized interstellar medium, is poorly understood. Some models propose that supernova feedback drives powerful outflows that carry metals out of the disk and into the halo, where they can be recirculated back down in the galactic fountain. Others argue that metals are trapped near their birth sites by magnetic fields, leading to a patchy, clumpy distribution. The most direct test comes from absorption line studies. When a distant quasar shines through the halo of a foreground galaxy, the atoms in that halo leave their chemical fingerprints in the quasar's spectrum. By measuring the abundances of different elements in those absorption lines, astronomers can map the chemical makeup of gas far from any star-forming region. These studies show that the circumgalactic medium, the halo of gas surrounding a galaxy, is often enriched to surprisingly high levels, suggesting that metals are indeed ejected from the disk. But the exact fraction of metals that escape, and how that fraction changes with the galaxy's mass and star formation rate, is still debated. The puzzle of chemical evolution connects directly to the origin of the elements themselves. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged in a star and then mixed into the interstellar medium before being incorporated into the solar nebula. The story of how those atoms traveled across space and time, from a distant supernova to the cloud that gave birth to our sun, is written in the chemical composition of the interstellar medium. Understanding the timing and efficiency of that journey is not just an exercise in cosmic bookkeeping. It is the key to explaining why the solar system has the exact mix of elements it does, and why life as we know it was possible at all. The more we learn about the chemical evolution of the interstellar medium, the more we realize that the elements are not simply produced and scattered. They are caught in a complex web of outflows, inflows, and turbulent mixing that spans billions of years and millions of light years. Every new observation of a distant galaxy or a nearby cloud adds another thread to that story, and every gap in our knowledge marks a place where the forgotten histories of atoms still wait to be uncovered. Half the metals made by stars have simply disappeared. When astronomers tally up all the oxygen, carbon, silicon, and iron that should be floating in the diffuse space between stars based on how many stars have lived and died, the numbers fall frustratingly short. This is the missing metal problem, and it is a ghost haunting every model of cosmic recycling. The metals are the heavy elements forged in stellar interiors and scattered by supernova. They should be spread throughout the interstellar medium, enriching the gas that forms future generations of stars and planets. But when we measure the abundance of these elements in the thin, diffuse gas that fills most of the galaxy, we find only a fraction of what we expect. Some estimates suggest that up to half of the metals produced over the lifetime of the Milky Way are unaccounted for. Something is hiding them. The most likely hiding place is dust. As we have seen, dust grains are built from exactly those heavy elements. In the dense, cold clouds where stars are born, silicon and carbon and iron stick to the surfaces of existing grains, growing them layer by layer. But even in the seemingly empty space between those clouds, a significant portion of the metals may be locked away inside tiny particles that are simply too small or too cold to emit much light. These grains are everywhere, yet they are nearly invisible to our telescopes except when they block or scatter starlight. Another possibility is that the missing metals are trapped in a phase of the interstellar medium that is extremely difficult to detect, such as the warm hot plasma we discussed earlier. At temperatures between 100,000 and 1,000,000 degrees, the gas is so thin that its emission is faint, and many of the metal atoms become highly ionized, stripping away most of their electrons. Those ions produce spectral lines in the ultraviolet and X-ray bands, which are hard to observe from the ground. Only space-based observatories like the Chandra X-ray Observatory and the Hubble Space Telescope can catch glimpses of them, and even then, the signals are weak and often blended with other sources. A third possibility is that the metals have been ejected from the galaxy altogether. Powerful supernova explosions and the winds from massive stars can drive gas out of the galactic disk, carrying the heavy elements with it. This outflow may then fall back in a galactic fountain, or it may escape into the circumgalactic medium, the vast halo of gas that surrounds the Milky Way. Observations of other galaxies show that such outflows are common, and they can remove a substantial fraction of the metals produced by stars. But measuring how much metal mass has been lost from our own galaxy is extremely difficult because we cannot see the full three-dimensional structure of the outflowing gas. The missing metal problem is more than just an accounting issue. It directly affects our understanding of how galaxies evolve. The amount of metals in the interstellar medium determines how efficiently gas can cool, which in turn controls the rate of star formation. It also influences the chemistry of planet-forming disks and the composition of the next generation of stars. If we are wrong about the metal budget, then our models of galactic evolution are built on a foundation that is missing half its weight. Astronomers are now using surveys of elemental abundances in stars at different ages to trace the history of metal production and loss. By comparing the metal content of old stars which formed early in the galaxy's history with young stars which formed recently, they can infer how much metal has been locked up in dust, heated into invisibility, or blown away. These studies show that the missing fraction varies from element to element. For instance, iron is often more depleted than oxygen, suggesting that different elements are removed by different processes. This variation gives clues about the physical mechanisms at work. Iron tends to condense into dust more readily than oxygen, so a larger fraction of iron may be hidden in grains. Oxygen, on the other hand, remains in the gas phase longer and may be more easily carried away by outflows. The puzzle is slowly yielding to new data. The Gaia spacecraft has provided precise distances to millions of stars, allowing astronomers to map the distribution of dust in 3 dimensions with unprecedented clarity. At the same time, new ultraviolet and X-ray observatories like the proposed Arcus mission aim to detect the hot, ionized metals that have been so elusive. And laboratory experiments are refining our understanding of how dust grains form and how efficiently they trap heavy elements. Every new piece of information tightens the constraints on where the metals could be hiding. But for now, a significant fraction of the elements that make up planets and people remain unaccounted for, wandering through the space between stars in a form we have not yet learned to see. The Galactic Center is where the extremes of the interstellar medium converge. This region, a mere few hundred light-years across, contains some of the most violent, chaotic, and mysterious gas in the entire galaxy. The magnetic fields there are thousands of times stronger than those in the space around the Sun. The turbulence is so intense that gas clouds move at speeds exceeding 100 kilometers per second, colliding with each other and shredding apart in just a few 100,000 years. The chemistry is bizarre. Molecules that are rare elsewhere, like silicon monoxide and iron hydride, appear in abundance, while carbon monoxide, the standard tracer of molecular gas, behaves unpredictably. And all of this sits in the shadow of Sagittarius, a star, the supermassive black hole at the heart of the Milky Way, a monster with a mass 4 million times that of the Sun. The interaction between this black hole, its outflow, and the surrounding interstellar medium is one of the deepest puzzles in astrophysics. When material falls toward the black hole, it heats up and releases a flood of X-rays and gamma rays, carving out a cavity in the surrounding gas. But the black hole is not always active. It seems to go through cycles of feeding and quiescence, and each cycle leaves its imprint on the gas around it. The mystery deepens when we consider the Fermi Bubbles, two enormous lobes of gamma-ray emission that extend 25,000 light-years above and below the Galactic Center. Discovered by the Fermi Gamma-Ray Space Telescope in 2010, these bubbles glow with a light that defies easy explanation. They are not produced by ordinary supernova remnants or pulsars. Their shape is too smooth and their spectrum too hard. Something else must be injecting vast amounts of energy into the galactic halo, and the leading candidate is a past outburst from the central black hole. Perhaps a few million years ago, Sagittarius, a star, went through a phase of intense activity, swallowing a cloud of gas and ejecting twin jets that inflated those bubbles. But the details of how the jet interacts with the interstellar medium, how it heats the gas to millions of degrees and accelerates particles to near light speed, remain poorly understood. The bubbles themselves are not empty. They contain hot plasma, cosmic rays, and magnetic fields, all of which must have been dragged out from the galactic center. The chemistry of the gas inside the bubbles is different from the rest of the halo, enriched with metals and showing unusual ionization states. Observations from X-ray telescopes like Chandra have revealed that the bubbles are surrounded by shells of cooler gas pushed outward by the expansion. Yet the exact mechanism of inflation is still debated. Some models invoke a fast, relativistic wind from the black hole, while others favor a slower, more gradual outflow driven by star formation in the central region. This puzzle is not just about understanding one bizarre structure. It is about how the most massive objects in the universe, black holes, can shape the interstellar medium on scales far larger than their own tiny event horizons. The energy released by a single feeding episode can blow gas out of the galaxy, alter star formation for millions of years, and leave a legacy that we see as the Fermi Bubbles. And this brings us to the final mystery, the one that ties everything together. The interstellar medium is not eternal. It is constantly being replenished by dying stars and depleted by star formation and outflows. Over billions of years, the balance between these processes determines the fate of the galaxy itself. Will the Milky Way eventually become a quiet, gas-poor spiral like the Andromeda Galaxy is predicted to become? Or will it continue to churn and recycle, producing new stars for trillions of years? The answer lies in the last and deepest puzzle of the interstellar medium, a question that reaches beyond our galaxy to the very end of the cosmic cycle of matter. The interstellar medium will not last forever. Every star that forms consumes a piece of that diffuse reservoir, locking gas away inside its core for millions or billions of years. When the star dies, some of that material is returned, enriched with heavy elements, but not all of it. A fraction remains trapped in the cooling remnants of white dwarfs, neutron stars, and black holes, permanently removed from the cycle. Over the long arc of cosmic time, the gas available for future star formation slowly dwindles. The Milky Way is already past its peak star-forming epoch. Billions of years ago, our galaxy was a furious factory, churning out dozens of new suns every year. Today, that number has dropped to just 1 or 2. And the trend will continue. In roughly 5 billion years, the Andromeda Galaxy will collide with the Milky Way. This merger will be a cataclysmic event for the interstellar medium. The two galaxies will plow through each other, their gas clouds slamming together at hundreds of kilometers per second. The compression will ignite a final, glorious burst of star formation, a brief renaissance where the combined gas is squeezed into dense filaments that collapse into stars at a furious rate. For a few 100 million years, the merged system, sometimes called Milky Way, will blaze with newborn suns and supernova, but that burst will be the last gasp. The merger will also stir up the gas, driving turbulence and heating it to temperatures where it can no longer cool efficiently. Much of the remaining reservoir will be ejected into the circumgalactic medium or even lost to intergalactic space. After the starburst fades, the galaxy will settle into a quiet, gas-poor state, dominated by old red stars and a thin, tenuous halo of hot plasma. The dense molecular clouds that once cradled star formation will be largely gone. The interstellar medium will become a ghost of its former self, a place where new stars are born only rarely, perhaps once every few 100 million years. This future is not certain. The details depend on the exact orbit of the merger, the amount of gas each galaxy brings, and the efficiency of feedback during the collision. But the broad outline is supported by observations of other elliptical galaxies, which are the end products of similar mergers. Those galaxies show very little cold gas and almost no ongoing star formation. They are red and dead, their interstellar medium reduced to a faint X-ray glow and a sprinkling of atomic hydrogen. The Milky Way's own interstellar medium, the subject of so many mysteries, will one day share that fate. And yet, even in that dim future, the story does not fully end. The hot gas that remains will still be enriched by the occasional supernova from old stars, and over immense timescales, some of it may cool and settle back into a thin disk. A trickle of star formation might continue, enough to keep a faint glimmer of life in the galaxy. The ultimate legacy of the interstellar medium is not a single, final state. It is a pattern repeated on a cosmic scale. Gas is gathered, compressed, ignited, scattered, and gathered again, each cycle leaving less material behind until the universe itself grows old. The mysteries we have explored, the missing baryons, the unidentified absorption bands, the hidden turbulence, the fate of the metals, the dance of feedback and collapse, all of these are the threads that weave that pattern. By understanding them, we see not only how the space between stars shapes the present, but how it writes the slow, patient story of the galaxy's decline and eventual quiet. And when you look up at the night sky, remember that the faint glow between the stars is not empty. It is the living, dying, and transforming substance that has built every world, including our own, and will continue to shape the cosmos long after we are gone. The universe keeps its secrets tucked into the spaces we thought were empty. From the missing baryons and the ghostly absorption lines to the hidden turbulence and the chemical dance on icy grains, every mystery we have explored reveals something deeper about the richness of the cosmos. The interstellar medium is not just a backdrop, it is the active, breathing engine that has built every star, every planet, and every atom in your body. And yet, as we have seen again and again, our understanding of it remains incomplete. Each puzzle is a doorway, a reminder that the more we learn, the more we realize how much we have yet to discover. The answers will not come easily. They will require the combined efforts of observers peering through next-generation telescopes like the Extremely Large Telescope, which will see the faintest infrared glows from the coldest clouds, and the James Webb Space Telescope, which is already rewriting the chemistry of star-forming regions. They will demand the power of the square-kilometer array, which will map the magnetic fields and tiny structures of the ionized gas across the entire sky. And they will need the persistent work of theorists and laboratory scientists, recreating the conditions of deep space in experiments that take years to yield a single spectral match. The journey is far from over. Every time a new instrument turns its gaze to the space between stars, it uncovers another layer of complexity, another hidden process, another invitation to wonder. So we ask you, the viewer, to be part of this ongoing exploration. Which of these 25 mysteries captured your imagination the most? Was it the identity of those diffuse interstellar bands, the fate of the missing metals, or the strange turbulence that shapes the birth of stars? Let us know in the comments below, and if you want to continue this journey into the unknown, make sure to like this video and subscribe to the channel. There are still more secrets hiding in the darkness, and we will keep following the light until we find them all.